Hello everyone, welcome to the PyCharm FastAPI tutorial series. In this tutorial, we will be focusing on deploying our application in Kubernetes. It is an open source container orchestration system for automating computer application deployment, scaling, and management. It was originally designed by Google and is now maintained by the Cloud Native Computing Foundation. So let's get started. For our tutorial, we will be using MiniKube. MiniKube is a tool that lets you run Kubernetes locally. MiniKube runs a single node Kubernetes cluster on your personal computer, including Windows, macOS, and Linux PCs, so that you can try out Kubernetes or for daily work. Let me tell you one thing, there are multiple ways to install Kubernetes and tons of tutorials available on the internet. You can check them out if you don't want to go forward with MiniKube. Also, I will be talking at a high level. We won't be getting a deeper dive into Docker or Kubernetes. As you know, these are subjects of their own, and I expect from the audience that they have experience working with these technologies. If not, I will share some links in my reference video where you can learn these topics separately. Let's begin by updating the system dependencies. After updating, I will install the MiniKube dependencies. Now I will download the MiniKube binary. I'll copy the minikube-linux-amd64 to /user/local/bin/minikube. I then make it executable. I then type the MiniKube version just to verify. Looks good. Next, I will install the kubectl, Kubectl, which is the Kubernetes command line tool. This allows you to run commands against Kubernetes clusters. You can follow the link shown on your screen. Once it has been downloaded, I will make it executable and move it to the user local bin so it's part of my path. We are done. Let's start the MiniKube, but before starting, I will create a folder in my home directory, which will be required for mounting for storing Postgres database files. Now I'm going to start the MiniKube. Oh, sorry, Docker is not there on our system. Let me install that quickly. I won't show the installation step of Docker because there are tons of tutorials on that. But I will share a good tutorial which I found in the DigitalOcean community. You can check that out. Okay, Docker has been successfully installed. I will retry again starting the MiniKube server, which will install the stable Kubernetes version. At the time of this recording, we are using Kubernetes 1.22. The installation will take some time. I will fast forward. The MiniKube has been successfully started. Let me verify that by typing kubectl get nodes. You can see that our single node is running perfectly fine. Now it's time to come back to PyCharm and write our Docker file. According to the Docker documentation, a Docker file is a text document that contains all the commands a user could call on the command line to assemble an image. We are using a Python 3.8 Slim image. The Slim image is a pared down version of the full image. This image generally only installs the minimal packages needed to run your particular tool. There's an interesting article in Medium talking about different Docker images. Do check that out. Line number 5 is going to create a group and a user. Next, we will move forward and create our app directory where we will copy our code. Following up, we will install system and Python dependencies. After that, I will copy the entire code, change ownership, and finally run the gunicorn process on port 5000. There are some cool plugins available for Docker and Kubernetes and PyCharm, which I forgot to mention. Let me quickly install them. The Docker plugin is already installed. Let me check for Kubernetes. We will use the Kubernetes plugin later, and I will show you how cool it is to manage pods through PyCharm. Before that, let's build our Docker image. The build process is complete. Next, we need to host this Docker image. So we will deploy this image in Docker Hub. Docker Hub is basically a Docker registry where you can store and share your Docker images the same way you store code in GitHub repositories. As you can see, I have already created the Docker repository, Currently it is private, but later I will make it public. As you can see, I already have an image with a tag as latest. Before pushing the image to Docker Hub, I will create a docker ignore file, which is similar to .gitignore. I will add some files and directories which won't be part of the Docker image. I will rebuild the image and provide the tag as shown in the Docker Hub. As we have already latest tag, we will create a tag with version 1.0. The image has been built. Before pushing, we need to authenticate our credentials. I'm going to type docker login and provide the username and password. Login succeeded. Now we are ready to push the image. The image has been successfully pushed. Observe the new tag 1.0 is now appearing. For our tutorial, I will be using the latest tag as it was working fine for me, no difference. I will change the visibility of the repository to public. If you have a use case when working with Kubernetes, you need to use images from a private registry, then definitely check out the documentation provided by Kubernetes. They've clearly explained in the documentation. We are done with the Docker file, and the image got built successfully, and we hosted the image in Docker Hub. Now it's time to play with Kubernetes. I'm going to create a directory in root and name it K8s. As you know, K8s is a short form of Kubernetes. Under the K8s directory, I will create multiple directories. First, I will create a namespace. In Kubernetes, namespaces provide a mechanism for isolating groups of resources within a single cluster. Names of resources need to be unique within a namespace, but not across namespaces. If you have observed one thing, all these files end with the .yaml, Y-A-M-L extension. The Kubernetes resources are created in a declarative way, thus making use of YAML files. Kubernetes resources, such as pods, services, and deployments, are created by using the YAML files. You can create resources with imperative commands, but it is suggested that declarative ways are much more flexible. Coming back, I will set the namespace to FastAPI-project. So all the pods, deployments, secrets will fall under this namespace. After namespace, I will create a directory and name it code, in which we will be writing deployment, services, and secret. Don't worry, at the end of this tutorial, I will explain the flow using a diagram. Let's move first with the deployment. A deployment is an object in Kubernetes that lets you manage a set of identical pods. Without a deployment, you'd need to create, update, and delete a bunch of pods manually. With a deployment, you declare a single object in a YAML file. This object is responsible for creating the pods, making sure they stay up to date, and ensuring there are enough of them running. You can also easily auto-scale your applications using a Kubernetes deployment. As you can see, we will be running 8 replica pods of our application, and Kubernetes will take care of that by checking the desired state. Kubernetes has a self-healing mechanism. It restarts containers that fail, replaces containers, kills containers that don't respond to your user-defined health check, and doesn't advertise them to clients until they are ready to serve. When working with Kubernetes, you're going to hear this word many times, and that is pod. A pod is the smallest execution unit in Kubernetes. Pods are ephemeral by nature. If a pod or the node it executes on fails, Kubernetes can automatically create a new replica of that pod to continue operations. Pods include one or more containers, such as Docker containers. You can see we have defined init containers. In Kubernetes, an init container is the one that starts and executes before other containers in the same pod. It's meant to perform initialization logic for the main application hosted on the pod. For example, create the necessary user accounts, perform database migrations, create database schemas, and so on. But over here, we're just checking whether our database server is up and running using the pg_ready command. Now under the container section, we will define the Docker image, which we have already hosted in Docker Hub. Image pull policy has been set to always. Every time the kubelet launches a container, it's going to pull the image from the container registry. After that, we're going to define a secret. We will implement this in a while. The container port is going to be 5000. Then we are going to do health checks using the readiness probe and the liveness probe. Readiness probes are designed to let Kubernetes know when your app is ready to serve traffic. Kubernetes makes sure the readiness probe passes before allowing a service to send traffic to the pod. The kubelet uses liveness probes to know when to restart a container. For example, liveness probes could catch a deadlock where an application is running but unable to make progress. As you can observe, we're using the HTTP GET request to check for the path/docs to return a 200 response at a period of 15 seconds. Next, we're going to define the memory limit to 512 megabytes and CPU, and expect it won't cross above that in case there is a memory leak. A container that requests 0.5 CPU is guaranteed half as much CPU as a container that requests 1 CPU. You can use the suffix "m" to mean milli. CPU is always requested as an absolute quantity, never as a relative quantity. 0.1 is the same amount of CPU on a single core, dual core, or 48 core machine. Next, we're going to create a secret. A secret is an object that contains a small amount of sensitive data, such as a password, a token, or a key. Secrets are similar to config maps, but are specifically intended to hold confidential information. Kubernetes accepts secrets as base64 encoded values. Encoding and encryption both are different. If you are interested in encryption, then check out Bitnami Sealed Secrets. We have provided the base64 values. I'll decrypt them and show you what values we are sending. Next, we're going to work on service. We could use a deployment without a service to keep a set of identical pods running in the Kubernetes cluster. The deployment could be scaled up and down, and pods could be replicated. Each pod could be accessed individually via direct network requests rather than abstracting them behind a service, but keeping track of this for a lot of pods is difficult, and this is where we introduce a service. A service is responsible for enabling network access to a set of pods. It doesn't matter how many pods come and go, the service is going to maintain a single IP address. As you can see, we have created a cluster IP service. Internally, we can talk with this service at port 5000. You can specify the type as cluster IP. Otherwise, it will be considered as a cluster IP only if you don't mention any type. There are many service types like cluster IP. This exposes a service which is only accessible from within the cluster. Node port. This exposes a service via a static port on each node's IP. Load balancer exposes the service via the cloud provider's load balancer. External name, this maps a service to a predefined external name field by returning a value for the CNAME record. We are done with the code part. Let's move forward with the web server configuration that is Nginx. I'm going to speed up the process. I expect you to check my source code as I have already provided all the YAML files. This is the Nginx deployment blueprint. As you can observe, we will be running 8 replicas of Nginx 1.21 version, and the container port is 80, and as usual, we're going to do the common health checks. We are using a volume mount to mount our configuration and replace the default configuration provided by Nginx. Next, we will define config map. According to the Kubernetes documentation, a config map is an API object used to store non-confidential data in key value pairs. Pods can consume config maps as environment variables, command line arguments, or as configuration files in a volume. If you observe carefully from line number 10 to 23, we are changing the Nginx configuration and proxying the request to the backend application. Line number 11 clearly shows that the request is going to the internal e-commerce service, which is running at port 5000. Next, we'll create the Nginx service, which is basically a node port service. Observe carefully from line number 13 to 15. We are using port, target port, and node port. Port exposes the Kubernetes service on the specified port within the cluster. Other pods within the cluster can communicate with this server on the specified port. Target port is the port on which the service will send requests to that your pod will be listening on. Your application in the container will need to be listening on this port also. Node port exposes a service externally to the cluster by means of the target node's IP address and the node port. As I said earlier, we have different service types, and the Nginx service is a node port service. In simple terms, we can access the pod externally through the port number 30009. We've completed the Nginx setup. Next, we will work on Postgres. As you can observe, for the Postgres deployment, we will only be running one pod. The container will be running on port 5432, and some memory limits have been applied. We will be introducing two major things: persistent volume and persistent volume claim. Volumes let you write your pod to a file system that exists as long as the pod exists. Volumes also let you share data between containers in the same pod. Persistent volumes exist beyond containers, pods, and nodes. A pod uses a persistent volume claim to get read and write access to the persistent volume. You can observe the persistent volume. We are creating a storage of 2 gigabytes in size. Also, the access mode is read, write, many. There are 4 types of access modes. RWO is read, write once. ROX is read only many. RWX is read, write many. RWOP is read, write once pod. We have set a reclaim policy to delete, and you have the option to retain as well. Deletion removes both the persistent volume object from Kubernetes as well as the associated storage asset in the external infrastructure. Storage class name is currently local storage, but you can also use AWS EBS storage, Google storage, etc. Observe carefully on line number 18. Path is basically pointing towards the directory where the Postgres files will be installed. If you are using Docker Desktop in Windows, then this is the way you need to provide the path, and the Postgres data folder is already present in the E drive. As you know, we are running our application on a Linux machine. And line number 26 will be replaced with MiniKube. So we need to provide the home directory path of the Postgres-data folder, which we mounted in the beginning when starting the MiniKube. Next, I will create the persistent volume claim. A persistent volume claim is a request for a resource with specific attributes, such as storage size. As I said earlier, a pod uses a persistent volume claim to get read and write access to the persistent volume. In our case, we are pointing to the volume name Postgres-PV. After we are done with volumes, we will create the secrets and services. The Postgres service is a clustered IP service, so we will only do internal communication. We are done with Postgres. Now we will move to Redis. Same as usual, we will create deployment and service files for Redis. We will run the Redis 6.2.5 Alpine image. The Redis service will be running on port 6379. We are done with Redis. Now we will move to Celery. It won't be having any service, only deployment and secret, because Celery will be used for processing the background tasks. You can observe that we are using a busybox image in our init containers just to do NSLOOKUP of whether our Redis service is present or not. Don't consider this as a health check. Observe line number 25. We will spin up a container from our backend image and execute the Celery command. Next, I will create the Celery secret. I will also decode the values and show you what I am passing. After we are done with Celery, I will create a job which will handle database migration. A Kubernetes job is a supervisor for pods carrying out batch processes. That is, a process that runs for a certain time to completion. For example, a calculation or a backup operation. I will create migration and secret YAML files. If you observe the code carefully, on line number 13, the migration command will run with a backoff limit set to 15. I will also check in the init container whether the Postgres database is running or not. If it's healthy, then only the migration command will run. Also, after 100 seconds, the job will expire. It doesn't matter whether the job was finished successfully or not. Finally, we have completed all modules which are required for Kubernetes. Let's now begin the deployment. I will open up the terminal and move inside the K8s directory. I will run a set of commands. Just follow along with me. First, I'm going to create the namespace. I'll type kubectl apply -f namespace. The namespace got created. After namespace, I will create Postgres and the other remaining modules. Something is wrong. Let me check what is being missed out. Oh, okay, I got it. The path needs to be /data. This is what we mounted when we started the MiniKube. Let me try again. And yes, Postgres is running now. Let me move forward and deploy the other remaining modules. Except for job, everything has been created. Let me now check the status of the pods by typing kubectl get pods -n FastAPI-project. As you can see, some pods are in the pending state, creation state, and some are still in the initialization phase. Let's wait for a few more seconds to see the progress. For your information, if your system has less resources, then try to decrease the number of replicas. Instead of running 8 replicas, try running with 1 or 2. As you can see, almost all the applications are running except e-commerce, which has 3 pending pods. And the reason behind this is insufficient CPU and our system is running low on resources. So I'm going to decrease the number of replicas for both Codebase and Nginx. As you can see, all the pods are running now. There are 3 backend pods, 3 Nginx pods, 1 pod for Redis, Celery, and Postgres. Everything looks good. There's one remaining thing which we haven't run yet, and that is the migration. Let's complete that. Yes, the migration has been completed. Let me now check in the browser. But before that, we need to retrieve the service IP address. If you are working with Docker Desktop and Windows, you can simply access it through localhost. But with MiniKube, we need to get the IP address. I will type MiniKube service list. And yes, the IP address is running on port 30009. That's 3 with 3 zeros and 9. The docs have been loaded. Let's test our API. I will create a new user and won't change anything in the request body. I care about the response. Yes, our user has been successfully created and we received the 201 status code and the entire stack is running in Kubernetes. If you are new to Kubernetes, then this video doesn't make any sense. But if you have already gotten an understanding of Kubernetes, then it would be very easy to conceptualize what I'm trying to do. Taking a small break, there's one more interesting thing that PyCharm provides. You can directly manage your Kubernetes resources through PyCharm instead of using the terminal. Let me give you a sneak peek. As you remember, we have already installed the Kubernetes plugin, and now we're going to check how it works. Click on View, then Tool Windows, then Services. You can check that it has detected the MiniKube. It has automatically detected the configuration. I will try to create a namespace. I'll click on this green play button, and it will execute it directly. As you know, we already have the namespace. Let me change it quickly. Now I'm going to deploy all the stack, but through PyCharm using the play button. You can even see the status of all the pods which have been deployed. Great part is that I can also see the jobs, deployments, services, cron jobs, replica sets, etc. This makes life easy by managing everything in one place. You can even see the persistent volume and persistent volume claim. There's one more thing provided by MiniKube, and that is the dashboard. I will type MiniKube dashboard in the terminal and press enter. This is basically the Kubernetes dashboard, the same way you can easily check all your cluster information. You will find more detailed information over here. Coming back to PyCharm, you can even follow logs of the specific pod, and you can open the shell as well. One last thing before we end this video. You can also change the kube config file. For example, if your cluster is running on a public cloud like AWS, or it's being self-hosted in an on-premises server, then you can easily communicate with the cluster by changing the kube config. So I hope you liked this video. If not, take some time. It's not a race. I will see you in the next video, where we will be talking about Helm charts.